Hello, game theorists. So we have the results from the Midterm 1 extra credit game. Here is the question so you can be reminded as to how it works. So you're paired with another student from the class. You both pick a number from 0 to 10. If you pick the same number, then that number is your payoff. So if you both picked 8, for example, each of you get 8. If you pick different numbers, then let's say H is the higher number and L is the lower number. The player who picks the lower number gets L plus 2. The one who picks the higher number gets L minus 2. So in our example, player A picked 0 and player B picked 1. 0 is less than 1, so 0 is the lower number. That means A gets 0 plus 2, the lower number plus 2, so they get 2. B picked the higher number, so they get the lower number minus 2. So 0 minus 2 is negative 2. That's B's payoff. So your extra credit points is just your payoff divided by 4. Because player A got positive 2, they get positive 2 over 4, which is 0.5. So student A is getting an extra 0.5% added to their grade for midterm 1. Player B got negative 2, so negative payoffs are possible, as you can see. Negative 2 divided by 4 is minus 0.5. That means player B would lose half a percentage point from their midterm 1 grade. So as you can see, there is a bit of risk involved with some of the choices here. So that's why I made extra credit. You don't have to play it. You aren't forced to risk anything. So first I want to talk about the Nash equilibrium. So we'll make a simplifying assumption here. Simplifying assumption is you only care about your grade. You don't care about cooperation or anything else. So if that simplifying assumption is true, and it might not be, but if it were, what do the players want to do? Well, the Nash equilibrium would be both players pick 0. Why is that? Well, you can see that each player wants to try to undercut the other player. So if your opponent picks 10, what you want to do is pick 9, right? If you undercut them and pick 9, you're getting the lower number 9 plus 2, so you'll be getting 11. So that's the biggest payoff you can possibly get. The person who picked 10, they picked the higher number, they're getting the lower number 9 minus 2, they're getting just 7. So if they pick 10, you pick 9, you undercut them, you get a payoff of 11. If they had picked 9 instead, what you want to do is pick 8. That's because if you pick 8, you get 8 plus 2, and 8 plus 2 is 10. So that's the best response to them picking 9. If you cooperated and played 9 as well, you'd be getting a payoff of 9 instead. But it's better to get 10 by undercutting them. So each player always wants to try to undercut their opponent. So if you keep this process going of undercutting, what would happen is it's going to just drive the choices down to 0. So if both of you pick 0, then it's a Nash equilibrium. No one can raise their payoff by playing differently. If you both pick 0, then your payoff is going to be 0. If you pick the same number, that's your payoff. You can't go below 0, so you can't possibly undercut them. If you picked a different number other than 0, that would make you worse off. So if they're playing 0 and you're playing 3, what's going to happen? Well, you pick the higher number, 3 is higher than 0, and you get the lower number, 0 minus 2, you get a negative payoff in that case. So if they're playing 0, your best response is to also play 0. If you try anything other than that, you'll get a negative payoff. By the same reasoning, if you're picking 0, their best response is to also play 0. That means that playing 0 is a mutual best response, so everyone plays 0 is the Nash equilibrium. Now again, that's all premised on you're trying to maximize your grade. Your actual payoff in the real world might take into consideration other things. We had that question on the practice session, where if one of the prisoners in the prisoner's dilemma has a strong sense of loyalty, and that loyalty is part of their payoff, then it could be rational to not confess. Likewise, if cooperation is part of your payoff, then cooperating and picking something like 10 could be rational if the payoff you get from cooperation is bigger than the payoff you get from a higher grade. So let's see what you guys did. So the most popular strategies in this game are what I call the Nash strategy, playing 0 like the Nash equilibrium would predict if you care only about your grade. That's one of the most popular strategies. The other most popular strategy is playing 10. If both players play 10, you get a payoff of 10 and both of you get 2.5% extra credit points. So both players going for 10 is the cooperative outcome. So there are cooperators who play 10 and there are Nash players who play 0. So let's look at what you guys did. So here is the histogram for this class. So you can see the most popular strategy here was the Nash strategy, playing 0. Though there was a substantial minority of you guys who tried to play 10. So because there are so many cooperators out there, is it going to be best in practice to play the Nash strategy? It turns out that for this class, you are best off playing the Nash strategy. So the average payoff for all the Nash players who are picking 0 was 1.6. They outperformed the cooperators who picked 10. So what happens if you're a cooperator is that sometimes you run into another cooperator and you both get 10, which is 2.5% extra credit points. However, more frequently, if you're a cooperator, you run into a Nash player who's picking 0 and you get taken advantage of. You get a payoff of -2 in that case. So there are so many Nash players out there that it dragged down the payoff for the cooperators. So the cooperators had a big reward if they met another cooperator, but more often than not, they got exploited by a Nash player. Now for Nash players, if a Nash player meets another Nash player, they're both playing 0, which means they both get a payoff of 0. However, if a Nash player meets a cooperator, then the Nash player gets a positive payoff because they're undercutting that cooperator. So it turned out that gave a bigger payoff for the Nash players. Now what's especially interesting about this class was that I played this game in class before with some of my previous pre-COVID face-to-face classes, and we actually got a different result there. Let me show you what happened in my last face-to-face class. So I played the same game on midterm 1, and in my face-to-face class, the most popular strategy was the cooperators, playing 10. The next most popular was the Nash players who picked 0, but you see the Nash players were in the minority. And it turned out in the face-to-face class that there are so many cooperators out there that the cooperators actually got a bigger payoff than the Nash players. Remember, if a cooperator meets another cooperator, they get a payoff of 10. So that benefit's pretty big, even though they sometimes meet a Nash player and get exploited. The Nash players benefit from undercutting the cooperators, but if they do so, if you're picking 0 and they're picking 10, your payoff's going to be just +2. So overall, the Nash players got a lower payoff than the cooperators did. So I thought it was interesting that, first of all, in real life, people do play some value in cooperation. We don't all play 0. There are some cooperators who play this game in the classroom. I thought it was especially interesting how cooperation was bigger in the face-to-face class. There's a twist I didn't really anticipate. I guess the online class feels more impersonal because it's just kind of the way things are. So that feeling of cooperation is just not activated if you're in that environment where you don't really know your classmates really well. So that's what happened in our midterm 1 game. I posted the results anonymously on Blackboard, so it's listed by your B number. So just look up your B number and you'll see how many extra credit points you got and what your opponent did in the game. So that's all for now. Take care and stay safe out there.